So we had 100 milliliters of water. If it increases 1 degree, then that would be 418 joules. But it increased 10 degrees, so that's 4,180 joules. Now this is a little bit of a simplification of the question that would likely be on the test. On the test, we'd probably say how many moles of reactant were neutralized, and so you'd have to come up with a heat of reaction. All right, here we go. Let's go to the next question. Let's see. Oh, Kieran Bernard is winning. However, wavy arm Kieran Bernard's winning more than the other Kieran Bernard. Okay.
Oh, must have answered first. All right.
Next. Carbon-hydrogen bond contains 430 kilojoules per mole of bonds. How much energy is required to break the bonds in 16 grams of methane? So there you go. You can phone a friend if you want. However, we have 16 grams of methane, CH4. How many kilojoules are required to break the bonds in 16 grams of methane? Oh.
Is this similar to the last one or no?
So the last one is just where the water is absorbing energy from reaction. This is where we're just breaking the bonds in methane. So this is so this is a bond energy style question. And you will be given the kilojoules per mole of bonds on the test all the time. So it's a bit of a throwback. All right. How are we doing? Kieran, you're locked in?
No, I'm just about done, sir.
Oh, okay.
There we go.
All right.
Let me just select the answer. All right, there we go. I'm good now.
Yeah, so we have 1 mole of methane. Each mole of methane has 4 carbon-hydrogen bonds. And so that means we have 4 times 413 kilojoules of energy released, because we actually have 4 moles of bonds. Okay, on to the, we're going to see who's winning. Kieran B, surprisingly enough, is winning.
Oh, thanks, Rogers.
All right. Is that home? So here we go. Hess's law question. We have those 2 reactions.
Mr. Rogers.
Yes.
Did the 16 grams even matter then in that question?
So it mattered because it told you that there was 1 mole of methane, right? So
yeah.
Carbon's 12, hydrogen's 4, so 16 grams per mole of methane. That means that we had 1 mole of methane. Okay. So the 16 grams definitely mattered. It told you how many moles were present indirectly. All right. So here we go. How are we going to figure out this question? This is just Hess's law. So be able to do Hess's law for the test. So there's reaction 1, reaction 2. How much heat is evolved in that reaction? So some people say these are a lot like algebra, and they're basically right.
How would you do it?
They're doing fatigue. I'm gonna brave it. I want to see what they're doing. Hopefully, yeah. Hopefully, it's background 5.
Rogers, how much was this? Like $400? It's something like this, but not a Zen book. Like, it's like the Vivo.
There we go. Any questions?
Yeah, how do you do it?
How do you do this? So this is Hess's law. So Hess's law just basically says, you know, if you've got two reactions that add up to make a third reaction, you can find the heat of the third reaction by adding the other two reactions.
Oh, so I don't need to do that switch around goofy crap?
Not in this case. No, this one's actually pretty simple. If you just
Oh,
look
I
at
can just do 180 plus negative 112.
well, I'm not going to say, but yeah.
Yeah, I messed up. I didn't do the negative. I should have picked the negative one.
Oh, look at that.
I know where I went wrong.
So how would we know if it was like the one where we have to like do all the switcheroo stuff?
So you'd have to do the switcheroo if one of your reactions has products that you want to be reactants, for example. So when you add everything together, basically you should wind up with something that has the reactants on the reactant side and the products on the product side. So if one of your reactions, your initial reactions that you're using to find the final reaction, if the products are on the reactant side, you're going to have to switch it around. All right, next question. Let's see who's winning.
Have you guys not been hearing me this whole time? I was muted for some reason.
All right.
Okay.
Are you, which Kieran Bernard are you?
I'm not going to say, Rogers.
Oh,
I'm the robot.
all right. Using standard enthalpies of formation is essentially the same as using Hess's law. True, false, or none of the above. Standard enthalpies of formation. Is that just Hess's law, but Hess didn't invent it? Is that true or false?
Essentially is a subjective term that you've used, Rogers. I don't know. I can't read your mind.
She just said.
I don't know.
What?
Because it completely depends on your definition of essentially.
All right. Basically the same.
I don't know which one you want, Rogers.
Oh,
You got 3 locked in.
there we
Oh,
go.
someone's had a bad day.
Yes, I have.
Oh, Kieran.
So yeah, standard enthalpies of formation, that's just Hess's law. What's the difference? Can anybody tell me the difference between standard enthalpies of formation and Hess's law?
Standard enthalpies of formation has to have elements as reactants, right?
That's right, elements in standard form. And that's the only difference between that and Hess's law. So once you know Hess's law, actually, if you know standard enthalpies of formation, Hess's law also makes sense. So we almost did it backwards. All right, here we go. Last one. Whoa, friendly neighborhood whiskey guy with a mustache. Moving up. All right, last question. Catalyst increases reaction rates by, get ready, shifting the Maxwell-Boltzmann distribution to the right, decreasing the activation energy required for a reaction, increasing the kinetic energy of the reactants, or increasing the surface area of the reactants. Okay, so all those things, they speed up the reaction. Which one is a catalyst doing? 2 out of 3 locked in. There we go.
Ooh.
Decreases the activation energy required for a reaction. So that's the function of a catalyst. When you decrease the activation energy required, you are going to have a lot more particles that are able to react in any mixture. How do you increase the kinetic energy of the reactants? What do you need to do?
Increase the temperature.
Increase the temperature, that's right. Increase the temperature, they bump into each other a lot more. A lot more of them will have the activation energy, okay? So a catalyst cheats the system.
Wait, so it was increasing the kinetic energy of the reactants?
No, it was not. That's what temperature does.
Was it the surface area?
No, that's what grinding up the reactants does.
Was it the Maxwell-Boltzmann distribution?
No, that's what increasing temperature does.
It was
right.
the activation energy required?
Correct, yes. That's the one that's marked in green.
But
Whoa.
Okay.